Hi everyone. A lot of people today. I actually didn't really expect that, so that makes me a bit nervous. But anyways, my name is Viktor. I'm 28 years old and I'm a senior penetration tester at Soul Cyber, where I mainly test web applications and APIs. I also do network penetration testing, recently mobile applications, and all other things related to cybersecurity. I was also a speaker at OWASP Bulgaria chapter, where I spoke about dependency confusion attacks, and at Softuni Cybersecurity Summit, where I basically spoke about basic web application attacks. And recently, I'm also a lecturer at Softuni. I have the following certifications, which are Junior Penetration Tester and the V2 version related to network attacks and basic web application attacks, Web Application Penetration Tester and Penetration Tester Extreme, Certified Applications Security Practitioner, and others. Also in my spare time, I'm a bug bounty hunter on several platforms, and I use Medium as my kind of personal blog where I can share all my findings in the bug bounty world. Today's talk is not going to go without some basics, so I'm going to try to break down JSON Web Tokens first, and then we're going to kind of deep dive into cryptography and potential mistakes that we can see. So, JSON Web Token, JWT or JWT, we'll look also at JWT, which are basically JavaScript object sign and encryption, which is basically a set of open standards which defines the JSON Web algorithms, JSON Web encryption, JSON Web signature, and JSON Web keys. So, we'll deep dive, as I said, into JSON Web Tokens. We'll basically have a look at three modern classes of JSON Web Token attacks, and these attacks you'll probably not see in any manual yet, because they are kind of recent, disclosed kind of recently, so this security research can give you a head start in your penetration test, or if you're a bug bounty hunter, or if you're interested at all in ethical hacking. So we'll talk about sign encrypt confusion and polyglot tokens. Both allow you authentication and authorization bypasses, or a complete token forgery. And we'll also talk about the billion hashes attack, which can be used for an application level denial of service against token processing servers. So let's look at a basic JSON Web Token. This one is in its most basic form. We have the JWT header, which defines the algorithm. In this one, there is no algorithm being used, which was actually related to a lot of vulnerabilities that we've seen with JSON Web Tokens. It's quite a famous attack, but it's actually part of the RFC, and this means that the JSON Web Token is basically not secured. We also have the payload, and the payload basically contains our claims. Claims are basically statements about a given entity. And in most of the cases, the claims are the entity is basically us, the user. So what is a JSON Web Token? It's basically a compact URL-safe means of representing claims to be transferred between two parties. As simple as that. There are two types of JSON Web Tokens, or at least two primary types, but we'll see also that there are others. So we have the JSON Web Signature, which is basically digitally signed. It can be symmetric or asymmetric. And we also have JSON Web Encryption, where the payload or the claims are basically encrypted. So this is a JSON Web Token in a JSON Web Signature format. We have the JWT header, as we said earlier. We specify the algorithm. In this case, it uses a hash-based message authentication code. So with a hashing function, so this is a basically symmetric JSON Web Signature using a secret. We have the JSON Web Signature payload. The payload is usually always the same. It always contains our claims. And claims are basically a key-value pair. The key is always a string, and the value can be any JSON primitive type. And then we have the signature in the JSON Web Signature, which is basically used to verify that the JSON Web Token was not changed during transit. When we create the signature, we basically base64 URL encode the header, the payload, and in this case, we have a predefined secret. Altogether, we use the hashing function to basically create the signature. This signature is then basically used to verify that the JSON Web Token has not been modified. Also, we have JSON Web Token in a format of JSON Web Encryption. So, in this case, we have the header, once again, but we have the algorithm and encoding. Both must be present in the header because we use the algorithm to basically calculate the content encryption key or to create the content encryption key. And we need the encoding to basically encode the ciphertext or the payload. And this is how we kind of create the payload. I'm not going to go into too many details here because this could be probably a lecture in itself. We also have the possibility of having a nested JSON Web Token, which is usually a JSON Web signature in a JSON Web encryption. So first, we create our JSON Web signature. Then we take that JSON Web signature and we use it as a payload of a JSON Web encryption, basically ciphertext. And it's kind of technically possible to first encrypt and then sign, but that could be an implementation mistake as well. That's why it's important to first sign the JSON Web Token and then encrypt it. And last part of theory, we also have JSON Web Key sets, which is basically a set of, it's basically a JSON representation of the public key in an asymmetric encryption. So in asymmetric cryptography, we have public and private key. In OpenID Connect, you'll see basically the public key being exposed. And this is how it looks. So as I said, there is usually a discovery endpoint where you can see it, but it's also possible to be calculated from two JSON Web Tokens. So if we have two JSON Web Tokens using asymmetric cryptography, we can calculate the public key. It has its own properties. I'm not going to go into details, but the properties will basically have the value of the public key. And here we're going to go into attack number 1, which, as I said, is sign and encrypt confusion. And before we get into that, we need to look at 3 distinct classes of cryptographic algorithms that we can use. So we have HMAC, which is basically symmetric cryptography. So you have only a secret. We also have digital signatures, which is public-private. So it's asymmetric cryptography using public and private keys. And we have authenticated encryption, which is how we create JSON Web Encryption. So the first two can be used to create JSON Web Signature. The last can be used to create JSON Web Encryption object. Now, which algorithm class we're going to choose depends on what we want to achieve. Any CISP holders or any CISSP candidates will know integrity, authenticity, confidentiality, and non-repudiation. So HMAC, digital signatures, and authenticated encryption all give you the integrity and authenticity of the data. In authenticated encryption, as you said, you also have confidentiality, which means that the payloads or the claims about a user, about an identity, or usually us, are confidential. They're encrypted, so they cannot be seen, which is, I guess, good if you need to put some sensitive data into the claims, like a password or something else. But what we actually want to look at here is the non-repudiation part, and kind of where many implementers of JSON Web Token libraries go wrong. And it's non-repudiation. Non-repudiation basically means that the data can be verifiable by others, which means that in a JSON Web Signature using asymmetric cryptography, the public key can be used to verify that the signature has been is actually valid. And this is kind of where we go a bit into code, and we're gonna look at an Authlib example, and this is all code from their website. It's not me writing it, so we'll kind of break it down. So we're basically importing the JSON Web Token object from Authlib's library, and we create a header and a payload. The header defines the algorithm RS256, and the payload, we have the issuer and the subject, which is usually us. We can load the private key, which reads a PEM file, and we encode it using the header, the payload, and the private key. But how we can verify it? We can basically load the public key that is related to that private key, and we can just decode it by taking the whole value of the encoded JSON web signature and checking it with the public key. From then, we can basically print the claims or print the headers, and we get basically the result. And we go into the more interesting stuff, basically, where when we decode in the way that we did here, when we load the public key and we decode the JSON Web Token with the public key, we can basically turn it into the dictionary of the payload. And what is interesting about this piece of code is that it's actually insecure. It's on their website, it's part of their documentation, but it's insecure. And the issue here is that we're basically not looking at the algorithm header. So when we're decoding, we can basically, what happens is the library basically look at the algorithm header, and based on the algorithm header, it will decide how to decode it. So you should never combine symmetric and asymmetric signature schemes. So your algorithm, you should usually have a check whether it's HMAC or whether it's asymmetric encryption using RSA, for example. So here we have a function on their website. Obviously, they tell us after this code, they say it's insecure, you shouldn't be doing that, and this is how you can do it, for example. So we have a function where we take the header and the payload. We look at the header, and if it's asymmetric, we return the public key. If it's symmetric, we return the shared key. And at the bottom, we basically decode, depending on the header, we're either going to use the secret or the public key. But let's say that we only want to use digital signatures, and we have RSA 256, 384, 512, which basically uses a different hash. But let's change the function a bit. So we still do the same that we do here, but we know that we're never gonna use symmetric encryption because we only have public and private keys. So we basically take the header and we check if it starts with RS. If it does, then we return the public key and we decode the JSON web signature. And here, that's where our vulnerability actually is, because yes, we will not allow algorithm confusion. You'll not be able to load a symmetric key. But what you can do is, instead of signing the token, we can actually encode it from a JWS. We can change the values here and turn it into a JSON web encryption object. So as you see here, we have the JSON web signature with your header, your payload, and your signature. We can change those values. This is basically done using JWT editor in BSides. So we encrypt it. We take the public key, which, as I said, is public, so anyone can get it. We use the public key. We change the key encryption algorithm to RSA OAP 256, and we specify the encoding that we're going to use for the JSON web encryption object. In the payloads, I've already changed roles from user to administrator. Once we encrypt it, we have the following object. And that's how our JSON web encryption looks. So you have your header once again, and you have your payload, which is now encrypted using the public key. So in this case, the JWT decode function will parse the algorithm header, and it allows all RS functions, which, once again, we're still within the category, right? It still starts with RS. And the claims validation is going to be handled by claims.validate, and that's how we actually get the sign encrypt confusion vulnerability. So what this allows us to do, we can basically forge a token, we can create our own claims, we can use it to basically become administrators. But the attack has some preconditions. So if you want to test it, first you need a library that supports asymmetric JSON Web tokens, so JSON Web signatures basically, which is almost every library out there. The application needs to use JSON Web signature tokens with public key cryptography. In our example, we used RSA, but it can be elliptic curve or any other public private key cryptography. And the private key needs to be accessible by the validation function. There should be no specific algorithm enforced. So if we go back to this piece of code, if we only allow RS-256, then this attack will not be possible because the algorithm is now not RS-256. And the attacker should be able to determine the public key. So we can either read it from the OpenID Connect Discovery endpoint, which is well-known /jwks.json, or we can compute it basically from two JSON Web signature tokens. That was attack number one. Attack number two is a polyglot token, which is actually very interesting. But once again, we need to go through some basics. And what we need to know is that there are two types of JSON Web Signature serialization, which is compact, and JSON serialization. And then there is also two JWS JSON serializations, which is general and flattened. The compact is what we've been looking at and what you'll probably see almost everywhere. And this is how a general JSON Web Signature serialization looks, where basically you have the payload and the signatures to the payload represented as a JSON object. And this is a flattened JSON serialization, where once again you have the payload, you have the protected header, you have the signature, and in this case we also have the key ID, which is not necessary, but it can be there. So we have interesting scenarios that happen in the wild, and it's when you want to transfer securely a JSON Web Token between two different applications. Now, here I've given an example of Azure, where you basically will need to be able to do that. And I've put some extra reading material if everyone wants to go through it. But I'm going to simplify it like this. So let's say that you have an application that takes two libraries, two JSON Web Token libraries. You use one library to validate, to basically do all the cryptography, and you only use the second library to do authorization decisions. You can do it for a number of reasons, and it actually happens more often than we know. So how it works is once we authenticate, we'll get the JSON Web Token, then we'll request a resource, we'll return the JSON Web Token in an authorization header. Library will look at it and say whether it can validate it or no. So if the signature is correct or no, then it will pass it on to the second library, and it will tell us whether we're authorized to access, let's say, the administrator portal. And here is actually a piece of code that is an example of what I'm talking about, where we have JWCrypto, which is the validator. So it will basically look at the signature, and it will verify whether the signature is fine or not. So it does all the cryptography. And then we also have Python JWT validator that will not do any cryptography. It will assume that the header payload have been verified with the signature, and it will only look at the claims and tell us whether we are authorized to do a specific action. So how can we exploit this? Let's say we have an authentic JSON Web signature in a compact format. Again, algorithm and the payload with our claims In this case, we are a John Doe. Now, what we can do is we can change the compact JSON web signature to a flattened JSON serialization format, where we basically, the protected will be the header, the payload will be the payload, and the signature will be the signature. But on top, we'll also add two new key value pairs. The first key is going to be, once again, the header, and then the value of the header will be a new claims payload that we create. In this case, we create new claims with the name of admin. We've set the expiry to 1 month later, and we've put a new subject ID. So what happens is, JWCrypto will look at this token that we've provided it, and it will ignore unknown fields. So the first fields are completely ignored, and it only looks at the protected, the payload, and the signature. It does the verification, and it's all fine. We have not modified the original JSON web signature at all. Once it verifies it, it passes it on to Python JWT. What Python JWT actually does is, it will take the header, the claims, and the signature, and it will split it on the dots, and it actually uses underscore, which, as put here, is basically a symbol commonly used to basically throw away a variable. So we're basically not going to use it at all. So what happens? It ignores all non-basics for characters, so that includes also the everything that's not in the basics for alphabet. So it will only leave us with the result at the bottom, where we have the header and the newly created claims. And this way, we've basically bypassed any authorizations that there were, and right now we're basically admin. And yes, that is attack number 2. And attack number 3, which is a bit more basic, but once again, we need to go into a few details. So billion hashes. In this case, we're going to look at the JSON Web Encryption. And once again, with JSON Web Encryption, you have 3 different ways to basically encrypt. You can use public-private key, you can use a secret shared key encryption, or you can use password-based encryption. And in this vulnerability, we're basically going to look at the password-based encryption. So how does it work? Key encryption with password-based encryption standard 2. We basically derive a key from a user-supplied password using the PBS2 schemes. So we can perform encryption of a content encryption key. As I showed you earlier, in a JWT, the content encryption key is used to basically encrypt the plain text or the claims. So there are 2 functions specified in the RFC, password-based key derivation function 1 and key derivation function 2. And the first version is no longer supported and is not recommended, so many libraries don't use it anymore. But we'll still look at the key derivation function 2. Now, it takes as an input a password, it takes as an input a salt, and an iteration count. How it works is, the encryption part, we take the salt and the iteration count, we select the length of the desired key length, and we apply all of this to the password, the salt, and the iteration count. Why do we want to do this? Because the more iterations it has, the less it will be susceptible to basically dictionary attacks. So think of it as in, let's say, Linux. You can have, for example, 10 iterations on a bcrypt hash, which means that you'll need more computing power to basically to be able to perform a dictionary attack, because each password you'll need to encrypt it 10 times to be able to get the same result. In a decryption, so we reverse the process. We basically need to provide the salt, the iteration count, and the password, and we and the key length, and we apply the selected function onto the password, and that's how we kind of decrypt the ciphertext. Now, the header parameters actually for PBS2 use the following. Those are the header parameters that are basically used for PBS2. We have once again the encoding, which we looked at earlier. We have the algorithm, which specifies the algorithm for password-based encryption standard with a specific hashing function. And we have additional header parameters, and these are actually the ones that we'll focus in. We have the salt input and the iteration count. So, as we can see, the iteration count is represented as a positive JSON integer. It needs to have a minimum iteration count of 1,000, or at least that is recommended. And this is actually where our attack comes in. It's as simple as that. We don't even need to know the token. We don't need to know anything. Basically, we can specify the algorithm. We can specify the salt and the encoding. And the rest of the JSON Web encryption objects can be absolutely bogus strings. It can be anything we want, because what actually happens here is we specified on the iteration counts a few billion of iterations. Now everyone doing some hashing functions will basically know that a few billion of iteration counts of a hashing algorithm will basically get a server or computer or anything down quite fast. So the server will basically need to compute all those billion hashes in order to be able to derive the content encryption key before it can determine that the JWT that we've provided or the JSON Web encryption is invalid. As I said, we can be unauthenticated. We don't need to have a valid token. We don't need anything. We just need to pass this as a header, basics for URL encoded, and then provide the rest of a JSON Web encryption. And this attack is mainly used against token processing servers, and the attack is not a normal network denial of service, it's an application level denial of service attack. So what was the result of all of those vulnerabilities? You have the following CVs and the following libraries that were affected. Now, we have the sign encrypt confusion 3 times on Authlib, JWCrypto JWX, which are actually very famous libraries for JSON Web Tokens. We also have the polyglot token vulnerability on Python JWT, which is what we actually looked at. And we have billion hashes attack against JWT and JWT JWT. Here I've listed the resources that I've used for the presentation. So if you like to go ahead and read some of this, trust me, it's very difficult reading, takes a lot of time. And probably most of you guys will be very bored at looking at RFCs. Anyways, it's actually quite interesting, and I think there is a lot to be learned. But yes, that was the presentation. Those were the 3 attacks that I wanted to present to you. And as I said, if there is any bug bounty hunters or penetration testers, these vulnerabilities are still almost not seen anywhere.